So in this video, we're going to cover the analysis procedure to calculate the moment of inertia. Alright, so the first thing that we need to know is we need to make sure we have to have y needs to be a function of x. Alright, so we have to be able to relate our x and our y values. Alright, so if this is true, we can set up an element with a finite length and a differential width. So you can do this in two ways. You can do a vertical or horizontal element where we have a finite length, in this case is x, and then our differential thickness or differential width is dy. Or you could have a vertical element where your dA would be equal to the height of this element y times the differential thickness or differential width of dx. Alright, so those are your two options. Either one is fine. Alright, sometimes it might be easier to define it one way or the other depending on your function. Alright, so in that case you want to determine I guess the last thing I'll note here is that the element that you draw, it should intersect the curve, the function or the curve at some point x of y. Right? So once we have our element defined, we can then look at, there's going to be two cases. So we want to determine I of x and iy. So we can determine I of x and iy. There's going to be two types of cases. The element is either going to be parallel with the axis of interest. So in the case of ix, in that case, when the element is parallel with the axis, this would be, for example, if we looked at figure A. Alright, in that case, we can use the original formula that we defined for our moment of inertia, which was for the x-axis was equal to the area integral of y squared dA. Alright, so what you notice here is that we have our dA term in this case is equal to x dy. So we could write this out as being equal to y squared times x dy. We'd have to convert x in terms of y, and we could then integrate. Alright, and then for I of y, we could do something similar, but instead of using figure A, we would need figure B. So you have the integral of a x squared dA. So you could say, in that case, it would be equal to x squared y dx. And then you had to convert y, would have to get converted to, as a function of x, so it should be easy to do, and then we could integrate. So in the second case is that if your element is perpendicular with the axis, you can still calculate I of x and I of y, but instead of using the original formula where we could just do a single integral, we need to use the parallel axis theorem. Right? So for our parallel axis theorem, we have I of x is equal to I of x prime, which is the moment of inertia of the element about its centroid, plus the a times d of y squared. Alright, so this would be for figure B, where we have the axis is perpendicular, the element is perpendicular with the axis, and then for I of y, we'd have a similar formula. We would have I of bar y prime plus a dx squared. All right, and both of these you can break into differentials as well. It could be, you could write this as dix is equal to di bar x prime plus dA cross dy squared, and then on the bottom for I of y it would be diy would be equal to d bar iy prime plus dA times dx squared. All right, so that's how you could calculate the moment of inertia using the element that's parallel with the axis and the element that is perpendicular with the axis.